Today's webinar agenda is the following. We will start by a short presentation of CLEARSY, followed by a reminder of some key elements related to functional safety, which are required for a correct understanding of the rest of the presentation. Then the main topic will be a detailed presentation of the CLEARSY Safety Platform, and more specifically, all the components in terms of hardware, software, and toolchain. Then I will explain how to use the CLEARSY Safety Platform inside a real industrial application. And at the end, we will have a conclusion followed by the Q&A session. So a few words about CLEARSY. So CLEARSY is a French SME founded in 2001 by the creator of Atelier B, which is an IDE used for formal development using the B-formal method. It's an independent company, because it's owned mainly by its employees. A few figures about the company. We made in year 2019 a turnover of 15 million euro. We have 4 offices in France, headquarters in Aix-en-Provence, and 3 other offices in Paris, Lyon, and Strasbourg. And we count about 140 engineers and PhD. A quarter of our turnover is made abroad in various countries. CLEARSY is also an historical partner of the RATP, French Paris Metro, for which we have developed and still developing systems that are used in revenue services. Our field of activities are the transportation, especially railway market, but also energy for nuclear power plants, for instance, and also defense. CLEARSY DNA is a designer DNA. So our core skills are divided into 3 main areas. The first one is the supply of safety system already developed and used in revenue services. We can adapt this existing system for specific customer requirements. The second field of business for CLEARSY is the design of turnkey safety critical system, certified system from a level from SIL 2 up to SIL 4. So we can take part of all of the scope of a project from system definition up to certification and deployment. So it includes hardware design and software design, hardware verification, validation, and software verification and validation, all the safety-related tasks, and also environmental qualification. We have also the capability of making prototyping of safety-critical system and also proof of concept in order to check whether a given technology is suitable or not for a safety-critical application. The third area in which we are doing business is the design of safety-critical software, especially by using the B-formal method, which ensure the generation of software which is bug-free related to its top-level specification. This method is used in order to design a safety-critical system like ATP in automatic metro, and used also by the major company within the railway market. With the B-formal method, we also perform data validation, so we check that rules expressed in a formal way, in a formal method, are meet or not within a large data set. And finally, we design also supervision and simulation system. Our expertise is focused on the Senelec standard and AREMA standard, so it's the standards for the railway industry. So Senelec EN 50, 126, 128, 129 for European country, and AREMA for North American countries. We are involved in a lot of projects related to light rail and metro, especially all the software used in CBTC systems, so ATO, ATP, and ATS. We are also realizing some signaling system based on PLC and relays for building interlocking. On the main line and the regional commuters, we have a dedicated department called ERSA in Strasbourg, which is in charge of providing solution and simulation tools for ERTMS. We have also performed signaling products for main lines. A few words about functional safety before moving to the main topic. So functional safety is a field of engineering. It's an engineering activity which intends to analyze, study, and reduce the risk for the people and the risk for the property on an industrial system. A few examples where functional safety matter is, for instance, the computer in an aircraft. If the computing unit fails and the plane crashes, then all the passengers will die. So in this case, the functional safety is obviously involved. Another example, maybe less obvious, is for fire monitoring system. If your fire monitoring system reports the wrong location for the fire ignition, then you may have a lot of loss in terms of assets if your building is destroyed by the fire or if you lost a monument, for instance. So it has huge impact in terms of cost for the company. The process of the functional safety is always the same. So it starts by analyzing all the hazards related to the system. Once this analysis is performed, we analyze the consequences of each of these hazards with one idea in mind, which is to assign a seal level to each function of the system. So seal level is a scale of integrity level, graduated from seal 0 to seal 4, where seal 4 is the most requiring level. And it indicates which is the residual risk that we are ready to accept. Once all the functions have been assigned a given seal level, an analysis of all the failures that can lead to this hazard and the associated consequences is performed. Usually in functional safety, we split the potential failures into two families. The first one is a systematic failure, and the second one is random failure. So systematic failure correspond to failures that exist since the beginning of the design of the system. It can be due, for instance, to a human error while writing source code, or a compiler error that translates wrongly one instruction into another. Systematic does not mean that the failure will reveal immediately when you start up the system. We can take, for example, one variable that trigger an hazard if its value is higher than 100. Let's say during the first years of use of the system, the variable is always below 100, but one day, due to external triggers or use case, the variable is equal to 101, and in this case, the hazard is triggered. On the other hand, the random failure only relates the fact that your system will wear out with the time. So it can be, for instance, a transistor inside an IC that fails short, leading to one pin of an IC always stick to a high state. Always stuck to a high state. Once all these failures are identified on the system, the purpose of the functional safety is to mitigate the risk by ensuring that the proper technological barriers or correct process has been applied, so the residual risk is below the previously defined level. At the end of the day, the end user of the system doesn't know anything about functional safety, but it's the motivation which allows him to take the train without fearing of a train derailment or without fearing that the train will collide with another train. We can now jump to the main topic of today's webinar, which is the CLEARSY Safety Platform. So the CLEARSY Safety Platform is a consistent and comprehensive framework which intends to ease the design and deployment of safety-critical applications and systems up to a seal 4 level. So it's composed of several parts in terms of hardware, software, and toolchain. I will give you a quick overview of each of them just now, and we will focus on each of these parts more in detail just after. So on the hardware side, the CLEARSY Safety Platform is made of a single board vital computer called CS0, which is an hardware target on which your application will be executed, and with an integrity level of seal 4. In order to help the learning curve of this vital computing board, and to also allow quick prototyping of your own interfaces, we provide a starter kit inside the CLEARSY Safety Platform. In terms of software, the CLEARSY Safety Platform is made of a vital software library, which provide all the built-in tests and features and functions that are needed for mitigating all the failure mode that may exist inside a computing unit. In order to integrate both hardware and software inside your final design, we also provide a toolchain which will help you to compile your application and also load it on the final target. And this toolchain is packaged inside a virtual image or a Docker container, which definitively simplifies the tool setup. One of the most important things to have in mind is that the CLEARSY Safety Platform is a solution ready to use and already certified against the latest version of the CNLX standard. So we get the SIL4 certificate from Certifer in January 2021. Even if the solution has been recently certified, it's a mature solution resulting from more than 10 years of innovation at CLEARSY. So all the principles that are embedded inside the CLEARSY Safety Platform have been already used and deployed on existing projects and products designed by CLEARSY. You have a quick list here of such products. So the first one is a platform screen door controller currently installed and used on the line 15 in Sao Paulo monorail, which has been certified SIL4 by Certifer. An equivalent system is also installed in Sweden, in Stockholm on City Line. It has been assessed compliant to SIL3 level by Bureau Veritas. And more recently, for one of our customers, we designed a remote I/O system for CBTC, which has a specificity of being certified for the European standard CNLX 1 and also for the North American standard, so the RMA 1. Which ensures that this system can be used everywhere in the world. We can now have a deeper view of each of the items of the CLEARSY Safety Platform. So the first one is a single board vital computer. So it's a small credit card sized board, which is powered by two microcontroller PIC32MX from Microchip. It relies on a composite fail-safe architecture, 2 out of 2. It means that if in case of failure of one of the two microcontrollers, the remaining microcontroller is still healthy and capable to maintain a safe state and also trigger the maintenance operation. Each microcontroller has a CPU capability of 80 MIPS, and the computing board consume less than 2 watts. So it will definitively help for the integration of this computer board inside your design. We made the choice to expose all the peripherals of each microcontroller to the end user. So as we will see just after, all the pins of each of the microcontroller are available on either pins on the bottom side of the PCB. So if we look deeper on the hardware architecture, we first notice that there is no power supply on the computing board. So it has to be provided externally by a motherboard that will carry the computing board. In terms of peripheral, we have only a few. So we have 2 LEDs per microcontroller that can be controlled through software by the end user. We have also 2 temperature sensors, 1 per microcontroller, which are used to ensure that the platform is used within its allowed temperature range. And finally, we have also 2 EEPROM memory, so non-volatile memory of 1 kilobyte each, 1 per microcontroller, that can be used for saving either application parameters of your custom application or authentication keys of each of the microcontroller. On the bottom side, you can notice that there is 2 connectors which are used to expose all the peripherals of the microcontroller to the motherboard. In order to help you to start using the platform and perform prototyping, we provide also a starter kit, which is a A5 paper-sized PCB, which embeds 32 digital inputs, 32 digital outputs. This starter kit is well suited for proof of concept because you have 2 header pins, two rows of header pins that are simply forwarding the pins of the microcontroller. So you can design an additional daughter board in order to prototype your own custom or specific interfaces. The interface with the development environment is limited to an USB plug So you can design your system with simply a laptop. Over this USB port, you have two debug interfaces, so two virtual serial ports that allows to retrieve information from each of the microcontrollers. And you have a few external plugs for I2C or UART. A quick summary on the hardware. So the hardware is composed of a vital computing board and a starter kit. So the vital computer board is already SIL4 certified. So if you want to design a new SIL4 product, you already have a SIL4 computer available. And it has to be seen as an integrated component. So you pick the component and plug it inside your final design. In order to start learning how the platform works and to prototype interfaces, you can use the starter kit. The advantages of this solution, it's more versatile than a PLC, because if you want to design something that has two analog inputs, three outputs, and one digital input, with a PLC mindset, you will have to buy one analog module plus one digital input module plus one digital output module. And here you can simply design everything on a single board, so it's more compact and it's more efficient in terms of costs. And you have no limitation in terms of count or nature of the interfaces. So if you have specific voltage or current, you can design the appropriate hardware interfaces. On the software side, the CLEARSY Safety Platform consists of a precompiled binary object library called CSP-lib. The development on the CLEARSY Safety Platform is performed without an operating system. So it means that you don't need to train your teams with a new or different real-time operating system. It's like from a software designer point of view, it's equivalent as designing on a regular microcontroller. This software library has in charge all the boot up sequence and microcontroller configuration, especially clocks, PLL, and various peripherals. Even if there is almost not a lot of peripheral on the board, a board-specific package is provided with associated drivers in order to have the capability to control the LED, retrieve temperature from the sensors, and also read and write on the EEPROM. It includes all the vital primitives that are needed for SIL4 development, especially all the vital voters functions, which are required to compare the results of both CPUs. And the most important part of this binary object library is that all the built-in safety health test, which ensure that the RAM is not corrupted, that the clock doesn't drift, that the memory program is not modified since the time you have flashed it, that the CPU is performing correct computation, and that all your peripherals are properly configured. What is important to notice here is that each of these services is automatically linked into your final application binary. So whatever you do, you cannot prevent the safety from being run, and it will result in a safe execution. And all these mechanisms are fully transparent for the final user in the sense that the only constraint is to call some function at a defined pace. Except this, all software architecture can be used. So you can have tasks or you can have a cyclic application. It's up to you. There is no constraint on these aspects. If we look deeper in the runtime architecture, we start from a source code written in B0, so it's the orange box on the sketch. And this single source code will be compiled with two independent and diverse compiling chain, resulting in two independent and diverse binary that we call replica. So each replica performs exactly the same features, but are diverse in the sense that they are not made of exactly the same sequence of instruction. Both replica are merged with the non-vital software inside the final binary, which is loaded on CPU 1 and also on CPU 2. So at the end, you have replica 1 and replica 2 on CPU 1 and replica 1 and replica 2 on CPU 2. What is important to notice here is that you have a single source code, so you don't need to have two independent software design teams written two equivalent softwares that are compiled independently inside two different languages. You have only one single input. The motivation of building two replica is basically to mitigate the failure mode of a computing unit. So replica 1 and replica 2 are executed from the same input data and produce two sets of output data, and they are compared. So we execute replica 1 and replica 2 in sequence, and this allows us to detect any discrepancies during the execution. For instance, if you have a cosmic ray or a RAM corruption leading to a variable corruption in replica 1, the result will be divergent with replica 2, which will be detected, and the system will reach a safe state. We are also performing cross-checks between CPU 1 and CPU 2 in order to mitigate all the remaining failure modes, especially clock drift failures, and also program memory corruptions. As you probably imagine, compiling two independent binary, merging them with non-vital software, and having a final binary ready to load on the target, it's not an easy task. So in order to help you for all these tasks, we have built a double compilation toolchain, which fully encapsulated the complexity. So all the complexity is fully hidden from the end user, and you simply have to define the list of your source files, and then run a command, and the final binary will be generated. You don't have also to manage the complex dependencies between the various compilers and tools, because everything is bundled inside a virtual container or image. So the dependencies are managed by CLEARSY. As you probably have noticed, the input language of the platform is B0. So B0 is a subset of the keyword of the B language, and this corresponds basically to the subset of instructions that can be translated for hardware. For those of you that are not familiar with the B-formal method and also with B0, the B0 can be compared to the C language without the pointer semantic, or to ADA language in terms of how complex it is to write. A quick summary on software and tools. So all the complexity of the software is fully hidden and transparent for the final user. So it's like developing regular software, but with the assurance of having a C4 execution. The execution is duplicated through replica 1 and replica 2, so for the vital software, I mean. And thanks to this architecture, all the random and systematic failure mode that exist or that might exist on computing architecture are mitigated. No installation is required. All the tool dependencies are automatically managed by the toolchain. Finally, the input language is B0, so it allows you to write software with any level of complexity. It's not like ladder diagram language where you are limited with coils and contacts. Here you can make branches and complex algorithms. We will see later in how to use the platform that B0 has also other advantages. At this stage, you have a clear view of what are the components of the CLEARSY Safety Platform. So we will now look on how we can use it on an industrial application. So if the remaining works when you buy a CLEARSY Safety Platform is the following. You have to design first the motherboard, which has the proper hardware for your interfaces or custom application. So the first point to notice is that you can mix vital and non-vital hardware interfaces and features on the same motherboard. You don't need to do only vital interfaces on the motherboard. You are fully free for defining the type of interfaces, the voltage, the current that you want to use on the motherboard. Depending on how your company is mature in terms of hardware vital design, you can design your own hardware motherboard, or you can ask CLEARSY for support for designing this motherboard. Once the hardware is built, you have to design the associated software, and here the software will be limited to the managing of your business logic and the drivers of the specific interfaces that you have built on the hardware motherboard. You don't need to work on how to secure the execution. Everything is covered by the C4 certificate of the CLEARSY Safety Platform. Finally, you will have to write the safety case of your application to show the compliance of your design with the standards requirements. So for this one, you will only have to perform the work for the custom parts, so your hardware motherboard and your software, your custom software for the business logic. Then you will have to show the compliance to the safety-related application condition of the CLEARSY Safety Platform to ensure that the conditions of the certificate are met, so you can rely on it. And finally, you will have to make a quick generation checklist, which simply consists of checking that the build has been performed with the correct library version and also the correct version of the tools. In terms of software design and validation process, several strategies are possible. So the only constraint is to develop the vital software in B0 language. Non-vital software can be developed in C language. And then you have basically two main options. The first one consists of writing your B0 manually, like you would have written in any other language, in your favorite language. So you don't use any formal method overhead. You don't have any formal method overhead. You write V0 corresponding to your vital software. The other option is to use the B-formal method and to refine an abstract model up to a B0 implementation. So this refinement activity can be either manual or automatically performed, depending of what you want to do, basically. A third option, if you have a lot of already existing legacy code, or if you are a software design flow for vital software already in place inside your company, one option could consist in designing a custom translator from your output of your current tools, so let's say Scale or Simulink, inside B0. And in this case, you can integrate the CLEARSY Safety Platform directly inside your design flow. So that's for the design of your software. In terms of validation, there are two potential strategies, depending of whether you use the B-formal method or not. So if you write B0 manually without any formal method, then you have to verify and validate your software according to requirement of the standards, especially CNLEC 50128, and it will result in performing unit test, modular test, and integration test. So it's something very usual in terms of software validation. If you select the formal method option, then thanks to the formal proof, the mathematical formal proof, you have the guarantee that your abstract model is properly implemented in the B0. So you only need to have abstract model review verification and some integration test. You don't need to do the unit test and modular test. So with the CLEARSY Safety Platform, you can use formal method development strategy, but you are not compulsory. But it's not compulsory. A quick example of what we can achieve with the CLEARSY Safety Platform. So it's based on our baseline product Saturn, which is a distributed I/O system. So we have several nodes. Each of them contain one CLEARSY Safety Platform plus a network interface. And on each node, you have some input or outputs. So in terms of performance, it depends of design trade-off. So I give one example here. With 12 instances of 12 nodes on the network, we can manage 176 SIL4 inputs and 88 outputs and have a refresh cycle shorter than 20 milliseconds. Usually on this kind of architecture, we have one node which is dedicated as a gateway to external devices, either for reporting states or receiving commands. We can also work in a closed system where outputs are simply controlled based on the logic of the inputs. A few words about availability, because we haven't addressed these topics so far. So the MTBF of the CLEARSY Safety Platform, so the single board vital computer, is more than 12 million of hours at 40 degrees Celsius. If this figure is not enough for your use case, then it's possible to build a redundant system. But you have to keep in mind that even if there is 2 microcontrollers on the computing board, these 2 microcontrollers are not meant for availability, but for functional safety. If one of the 2 microcontrollers fails, then the whole computing board will shut down and keep the safe state. So you cannot work with only 1 microcontroller out of the 2. If you want to have a redundant system, you have to duplicate the whole computing unit. A conclusion on this topic. So the CLEARSY Safety Platform is already certified, so you can take it inside your design, and it will help you to design SIL4 products, because you only have to focus on your custom parts, so business logic software and dedicated hardware for the interfaces. It results as a shorter time to market and also limited effort in terms of V&V, because you don't need to validate the correctness of the execution inside the computing unit. If you make the choice to use the B-formal method, which is an opportunity with this platform, then the V&V effort will be more limited, because you only have to do the formal specification review and integration test.